Bismillahirrahmanirrahim. Assalamualaikum and very good day to you all. Okay, we are coming to the last slide on the chapter shaft. We are talking about stress and torque capacity in interference pits. Okay, again, this chapter is taken from the book Shigley Engineering Mechanical Design, and all the images is taken from Google Images. Okay, Okay, talking about interference pits. Okay, interference pits to minimize the need for shoulder and key weights. So, what is exactly an interference pit? Okay, suppose for the normal operation, you have a shoulder like this. This is the called shaft shoulder. The mechanism that is this is a shaft shoulder. So, what about you don't want a shoulder because shoulder have space. Here, this is a space. So now the space is limited. You don't want to get a big space, okay? Just want to get a shaft, only a shaft lah, okay? So what you're going to do is to make it a fit, okay? Interference fit, as you can see in this image, okay? This is maximum interference, meaning the shaft and the hole. The shaft is bigger than the hole. When the shaft is bigger than the hole, it cannot go in. Okay, it cannot go in. So it cannot go in. How can you make the shaft go in a small hole? Okay, so this is called the interference piece, meaning that one portion either you put fire, you burn it, you burn the hole or the shaft, or another one you put ice, make it when the ice when you put the ice, it will become shrinking. When you put ice, become shrinking. Okay, so you can put the hole into the shaft, or you burn the shaft to make it bigger. Okay, because a material property, if you burn will make it bigger. Okay, so this bigger, you can put the ice in, you can put the shaft into the small hole. Okay, that's the trick. Okay. Okay, the stress equation in this situation is developed in section 316. You can see here I have taken the portion of the section 316 here. It is called press and shrink pits. Okay, if you have time, you go have the, and also you have the book, you go to this chapter 316 to study more. Okay, this is the pressure at interface of interference pits, meaning that let's say this my my pen. Okay, this is the hole, this is the pen. Okay, you put it into the pen. Okay, the pressure at this point. Okay, whether the pressure at this point, what is the pressure at this point of contact? Okay. Okay, usually most of the time it is made from different material. This is different material, this is different material, but some also it can be made from the same material like this. This is plastic, this is all plastic, the same plastic. Okay, it made from the same material. Then you have equation. You have this equation for the different material, and this equation for the same material. Okay, to get the pressure at this point, the point of contact. Okay, now we're talking about the maximum pressure on the tolerance. Where is the maximum pressure? Here, let's say for this case, this is the case pen cap. This is the hole. This is the shaft and going inside it. What is the maximum pressure here? Okay, it depend on the this on the deviation. Okay, deviation minimum and deviation maximum. Where do you put this? You remember in the last slide? Okay, you scroll, go back to the slide. It is the equation is like this: P equals to Young modulus time deviation, okay, plus 2D. This is the diameter. Okay, this is the uh, diameter or for a shaft because it is a small d. So diameter or shaft, and this is what we are talking about. from this slide, the minimum, the maximum, uh, deviation minimum and deviation maximum. You get from this, slide. Okay, you get from this answer, and you put the answer in this question, in this equation, and you get the maximum pressure. Okay. Okay, now we're talking about tangent stress and also the radial stress. In the next slide is the slide for radial stress. Okay, but the explanation is the same. Okay, okay. About tangent stress, when you see this is a shaft, where is the tangent? The tangent is the tangent direction, meaning that if I represent to you this shaft, it is at this point. Okay, it is at this point. So the normal distribution is not in this slide, but it's a normal from, meaning that normal from this. Okay, normal from this shaft. Okay, and we're talking about radial stress. What is a radial stress? It is easy to explain radial stress because uh, your house, sure you have um, gas tank. Okay, for cooking. Okay, for cooking, the pressure inside the gas tank is a radial stress. Okay, also when you um, cook the water is heating. Okay, the water is heating inside the kettle, all the pressure inside the kettle going up onto the kettle. Okay, if that kettle cannot withstand that pressure, the kettle will burst out because of the exceeding radial stress. Uh, okay, this is the explanation for radial stress, which in the next slide. Okay, for the tangent stress, meaning that the force at the surface of the, or the not the force, the stress at the surface of this shaft, whether it can withstand or not withstand the load given onto the shaft, especially when the shaft is rotating. Okay, so this is some explanation for the tangent stress. Okay, just like I said in the last slide, about the radial stress, is the stress inside going up, because the nature of any material, when you put the material inside it, in the nature will be going force out. Okay, it's the nature of the material is going to force out. Okay, especially if you imagine when you are cooking water. Okay, boiling water, you are boiling water, the water expand, the water expand through the surface of the kettle, and if the kettle cannot withstand, it will burst out. Okay, there is an easy explanation for the radial stress. Okay, tangent and radial stress. How is its relation to the failure theory? Okay, it says that here, um, if the either shaft or hub yields during assembly, full pressure will not be achieved. What is the full pressure? Meaning that this is, okay, again, I give example with the pen. This is the pen. This is the a shaft. This is a hole. This is a shaft. When going into this hole, both are not fail. You do not see any whether this hole or this shaft fail during this assembly. So it has full pressure going inside it, and take a quite strength to make it going up and make it going down. And when I uh, make it like this, the cap doesn't go down. Okay, what does it mean by uh, the shaft fail? Is that like this is the cardboard. Okay, of course cardboard. Okay, let's say I put the load and this cardboard going like this, it meaning it fail, it cannot get the full pressure. Okay, this is example and analogy failure of a shaft, okay, failure of the hole, meaning that if this one portion fail, it cannot give a full pressure, and maybe if I put the cap here, the cap will going down, okay, will go down because this portion cannot withstand the load. Okay. Okay, let me explain about three-dimensional stress element. Okay, it says that in this first paragraph, the stress element on surface of rotating shaft will experience a completely reverse bending stress. What does it mean by reverse bending stress? Okay, here is a shaft. Okay, and it rotates. And when it rotates, what is the force? Actually, what happened when it rotates? When it rotates, it actually bending now. Okay, bending, going up, going down, going up, going down, all the time. Up, down, up, down, up, down. When you go up and down all the time, it is reverse. Meaning that don't have to calculate bending because bending going up and bending going down is the same value, then don't have to calculate anymore. Okay, plus minus will give the same uh, we gain the same equal, equal because it go when it shaft it rotate, it going up and down all the time, bending, upper bending, lower bending, upper bending, lower bending. Then don't need to calculate bending. Okay, and then the second statement, since shear stress due to torsion may be present, the stress value do fatigue press compressive the fatigue situation is actually be improved. Again, I give the example for this my pen and cap. Okay, it is a press fit. It's a press fit. I press, then it fit inside it, and the cap is not going down. Okay, accidentally not going down, and then fatigue situation happen when the structure is long. Okay, this cap, and when the structure is long, okay, and then it is attached to something like this, the fatigue will be diminished. Okay, the fatigue will be diminished because it is compressed. Of course, I give some compression inside it. Okay, if given like this, okay, nothing happen, then it will become fatigue. Okay, it become going at a long time, no action happen, then the fatigue failure will happen like this. Okay, at this point, so I give the support here, compress, so fatigue will be improved. It will eventually become fatigue, but it's, for the time being, it's not becoming fatigue. Okay, so problem solved. Okay, stress concentration factor, the design of hub geometry, and therefore its uniformity and rigidity can have significant impact on the specific value of stress concentration factor, making it difficult to report generalized value. For first estimate, values are typically not greater than 2. Okay, so when you do some calculation, the K factor, if you remember the stress concentration factor, the K value must be less than 2. Okay, you see the sharp edges, this is a sharp edges. Okay, okay, meaning that try to avoid this because these sharp edges will be give the result over 2, K over 2. Okay, meaning that you should have fillet. Okay, the fillet. Okay, better have fillet. Okay, so the fillet K factor low than 2, so okay lah. Kan? Torque and friction on interference mean. Okay, torque and friction is related. Friction is happen anywhere. Okay, happen anywhere. Everything has friction. Okay, this pen I'm holding. Okay, the thing that prevent it to become fall down is a friction. Okay, the thing that make it hard to me to put, okay, inside this is also friction. Okay, this pen this size okay, when I going pen into this cardboard, okay, is no friction because the friction is only from the air, but it can be neglected, okay, because it can easily go up and down all the time. It's no friction happen, okay. So the force is at times with the friction force, friction time the force with the normal force, get this equation by FPLD, okay, which is pressure, length and diameter, and this is the torque, okay. Torque the torque original equation for the torque is torque equals to force times radial, okay. Force, everything have friction, so you add the friction value, torque friction, torque friction equal to friction force friction, okay, times the radial, okay. So remember, everything have friction, okay. Don't forget friction. So is the end of this lesson for shaft. I hope you all will get benefit from these videos. There are 22 videos talking about shaft, and for better understanding, it is better you purchase the textbook from any bookstore, uh, because you will use this information from the textbook throughout your working life, okay. It's not for only stop at university. When you are working, you may use this knowledge and you may refer for the textbook, okay. That's all for the lesson for shaft. We will continue in another lesson, okay, in the next video, in the next session. So thank you very much. So see you all again, okay. Goodbye.